Hello again, and welcome back to Project Metamorphosis, where we explore the deepest questions about the future of humanity, technology, and everything in between. Before we dive into today's episode, do us a small favor: like, share, and subscribe. To support the project, your support helps us keep digging into these complex, fascinating topics and share them with the world. Now, let's begin. Quantum computers are useless. That's the claim echoed by skeptics, critics, and even a few frustrated physicists. They say quantum computers are all theory, all hype. No real-world application, no practical use, no breakthrough moment. But what if they're wrong? What if the very concept of usefulness is shifting right under our feet? To understand this, we must begin with what makes a quantum computer different. Traditional computers operate using bits, zeros and ones switches that are either on or off. Every app, every email, every simulation you've ever run depends on those bits. But quantum computers use qubits, quantum bits that exist not just in one state but in superposition, being both 0 and 1 at once, at least until observed. This is not science fiction. It's quantum mechanics, the most precisely tested and experimentally verified theory in physics. The power of quantum computing comes from this counterintuitive behavior, where information doesn't just exist in discrete chunks, but as a cloud of probabilities, interacting in ways classical systems can't replicate. So when critics say quantum computers are useless, they often mean they don't behave like classical ones. They expect linear improvements. But quantum computing isn't about gradual gains. It's about exponential leaps. For instance, a quantum system of 300 qubits can represent more classical states than there are atoms in the observable universe. Imagine the computational landscape that opens up when we can manipulate such a state effectively. Not for running Netflix or checking email, but for problems like simulating complex molecules, solving optimization puzzles, cracking encryption, or even generating entirely new materials. But here's the twist. Even in their primitive form, quantum devices are already showing signs of capability. Recently, researchers demonstrated that quantum systems could produce random bits, genuine randomness, not the pseudo-randomness we use in conventional computing. While that may sound trivial, randomness is a backbone of secure encryption, simulations, and probabilistic modeling, and true quantum randomness can't be reverse-engineered or predicted. It's baked into the universe itself. So yes, some of these quantum outputs seem random or chaotic, but randomness isn't useless. It's raw, foundational, and, when understood, profoundly powerful. Take quantum supremacy, a term coined when Google claimed in 2019 that their 53-qubit quantum computer had performed a task in 200 seconds that would take a supercomputer 10,000 years. Was the task useful? Not really, but that's not the point. It was proof that quantum advantage is real and measurable. That milestone, although controversial, was a shot across the bow of classical computing. It showed that quantum behavior can be harnessed, even if just barely, for tasks beyond classical reach. Still, scaling quantum computers remains an enormous engineering challenge. Qubits are fragile. They decohere when they interact with the environment. They need to be kept near absolute zero, and they're prone to errors. Error correction alone may require thousands of physical qubits to create one reliable logical qubit. But the fact that we've started generating bits at all, from a system designed to function with uncertainty, is nothing short of historic. These aren't just random outputs. They're the beginning of quantum information. And history shows us something important. Early technologies are always misunderstood. The first electronic computers were the size of rooms and had less processing power than a pocket calculator. The internet began as a military experiment. AI was a curiosity. And yet, each of these reshaped civilization once the right infrastructure and insight caught up. Today, it might feel like quantum computers are toys, but that's how revolutions begin. They start in laboratories with strange results and skeptical audiences. Then, inch by inch, the world shifts. It's not about replacing your laptop. It's about redefining what's possible when information is no longer limited to classical constraints. In that sense, the generation of random bits from a quantum device isn't the end of the story. It's the first coherent sentence in a language we're only just beginning to learn. Coming up, we'll explore what quantum randomness actually means, how it's measured, and whether this so-called uselessness might be the most powerful signal we've ever received. Now, what exactly do we mean when we say quantum computers generate random bits? At first glance, randomness might seem like noise, useless, chaotic, without structure. But in quantum mechanics, true randomness is sacred. It's not just a byproduct, it's a fundamental feature of the universe. Quantum randomness emerges from the collapse of a wave function, the instant when a quantum state settles into a definite outcome. Unlike classical systems, no algorithm or hidden variable can fully predict the result. That has profound implications. For one, quantum randomness enables unbreakable encryption. In quantum key distribution, QKD, two parties can share a key generated from entangled particles. If a third party tries to intercept it, the very act of measurement disrupts the quantum state, alerting the original users instantly. That's not just secure, it's self-defending, and the utility doesn't stop there. Many modern systems, from financial simulations to climate models, rely on Monte Carlo methods which demand large quantities of random numbers. Classical methods. Try to approximate this with pseudo-random generators. But if your randomness isn't truly random, the results can be subtly skewed. Quantum randomness fixes that. It brings authentic unpredictability to systems that depend on it. Even more importantly, quantum computers are opening doors into questions of reality and causality. In the classical world, every event has a cause. With enough data, you can forecast outcomes. But in the quantum realm, this isn't always true. Some events don't have a why, they just happen. It's not ignorance, it's fundamental indeterminacy. This isn't just a curiosity. It's a revolution in how we think about cause and effect, determinism, even free will. The fact that we are now building machines that rely on this strangeness, that require it, is astonishing. It shows that we're not merely theorizing about quantum mechanics anymore. We're engineering reality based on its principles. Of course, this engineering is difficult. Maintaining coherence, reducing noise, correcting errors. Quantum computers are fragile. They need near-perfect conditions to function. It's like trying to balance a pencil on its tip in a hurricane. But the progress is real. From superconducting circuits to ion traps to photonic qubits, researchers are pushing every boundary to stabilize and scale quantum systems. And now that we've seen successful generation of quantum bits, even if they're simple or random, we're no longer speculating. We're witnessing the first computational expressions of this new paradigm. Just as the earliest classical computers once filled rooms to solve arithmetic, today's quantum systems are clumsy, but historic. They represent the birth of a new form of processing, one that doesn't just compute differently, but redefines what computation can be, and this is only the beginning. Coming up, we'll dive into what quantum algorithms mean for the future, how they work, what they promise, and why even the smallest breakthrough in error correction or coherence time could unlock computational abilities that outpace anything we've seen before. To grasp the magnitude of what quantum algorithms could accomplish, consider Shor's algorithm. In classical computing, factoring large numbers is hard, so hard, in fact, that it forms the basis of RSA encryption, which protects most of our digital communications. Shor's algorithm, running on a sufficiently powerful quantum computer, could crack these cryptographic keys in a fraction of the time. What once took millions of years of classical processing could shrink to minutes. This isn't just a party trick. It's a tectonic shift in security, commerce, and trust. Another landmark, Grover's algorithm, which offers a quadratic speed-up for database searches. That might sound modest, but when you scale up to massive datasets, the impact is huge. It means faster AI training, quicker pattern detection, more efficient resource allocation. But the really exciting possibilities aren't just about speed. They're about possibility itself. Quantum computers can simulate quantum systems natively. That's like asking a fish to describe water. It's built for it. Classical computers struggle to model molecules or atoms because the number of variables explodes exponentially. But for a quantum system, that complexity is natural. With quantum simulation, we could design new materials from scratch, superconductors, biocompatible nanostructures, custom molecules for medicine or energy. This opens up a future where drug discovery becomes proactive. Instead of trial and error, we could simulate how proteins fold or how compounds bind to receptors at the atomic level. Months of lab work could be replaced by simulations done in hours, and it doesn't stop there. Finance, logistics, transportation, any field involving complex optimization stands to be transformed. Quantum annealing and variational algorithms might one day navigate trillions of variables to find the most efficient path, strategy, or allocation. But we're not there yet. Today's quantum machines are noisy, intermediate-scale quantum devices, or NESQ for short. They're powerful but limited. Coherence times are short. Error rates are high. Scaling up qubits introduces new noise. It's like trying to write a novel while someone erases letters every few seconds. And yet, even in this noisy realm, we've already demonstrated quantum supremacy. Tasks where a quantum machine outperforms any classical counterpart. That's a milestone. Not a full revolution, but a proof that the foundations are working. So why do some still claim quantum computers are useless? Because at this stage, they can't yet replace classical systems. They complement them, they reveal new potentials, but they aren't ready to handle your emails or stream videos. Much of their power is still theoretical, their practical applications nascent. But here's the thing. So was the internet once. So was electricity. Every transformative technology starts small, expensive, and misunderstood. The same voices that mocked early computers, those that took up entire buildings to compute simple math, are now echoed by those who dismiss quantum progress. It's a familiar pattern in the evolution of paradigm-shifting tools. So what does the path forward look like? For one, hardware must improve. Qubits must scale and stabilize. Researchers are exploring topological qubits, trapped ions, photonic systems, all racing to find the balance between control and scalability. At the same time, software must evolve. Quantum programming is still in its infancy. Languages like Qiskit and Cirq are laying the groundwork, but a new generation of quantum-native coders is essential. These minds won't just translate classical ideas, they'll invent new forms of logic and interaction. And perhaps most importantly, we need to redefine what useful means. If a quantum system helps solve one crucial problem, designing a clean energy material, optimizing vaccine deployment, simulating a planetary climate, that alone could justify its existence. Its value won't lie in replacing classical computers, but in doing what they cannot. In the next section, we'll explore how these capabilities could radically reshape industries, economies, and even the way we think about intelligence, both artificial and human. Stay with us. Imagine a world where quantum-enhanced AI becomes part of the standard decision-making pipeline. Today's AI models are powerful, but they're bound by the limits of classical computation. Training large language models or simulating intelligent agents takes vast amounts of energy and time. Quantum acceleration could reduce that cost drastically. This fusion, AI and quantum computing, isn't just additive. It's multiplicative. AI helps quantum computers by optimizing error correction, guiding qubit calibration, and enhancing measurement strategies. Quantum computing helps AI by opening new pathways for parallelism, more efficient learning, and better optimization landscapes. It's a feedback loop of innovation. Now apply this synergy to healthcare. With quantum-enhanced AI, we might be able to simulate entire biological systems, not just a protein, not just a cell, but a whole immune response, a full organ interaction, a digital twin of your body. Treatment plans wouldn't be standardized. They'd be tailored in real time, simulated and adapted continuously to your biology, your behavior, even your microbiome. Finance is another sector bracing for impact. Portfolio optimization, fraud detection, risk modeling, all thrive on complex computation. Quantum processors could crunch scenarios no classical system could, offering not just speed but depth, a deeper understanding of market complexity, Behavioral patterns, systemic risk, even urban design and logistics could transform. Traffic optimization in megacities, energy grid management, water resource planning. Every system with millions of variables and constraints could become fluid, self-correcting, adaptive. But there's a deeper transformation on the horizon: our relationship with knowledge itself. We've long relied on deterministic logic, cause and effect, input and output, binary decisions. Quantum mechanics breaks that mold. Superposition and entanglement imply that the universe is not binary, but probabilistic, contextual. As quantum computation matures, we may find ourselves rethinking logic. What if the next generation of computers doesn't give us a single answer, but a spectrum of possibilities? What if intelligence isn't about reaching a fixed conclusion, but navigating uncertainty with grace? That redefinition could ripple through everything: science, ethics, education, even spirituality. We'll have to ask new questions about truth, trust, and agency. If a quantum-enhanced AI suggests a medical diagnosis, but we can't trace its reasoning classically, do we trust it? If a quantum simulation offers a new climate policy, but we can't verify every step, do we implement it? These aren't theoretical puzzles. They're philosophical frontiers we'll face in practice. And then, of course, there's governance. Quantum supremacy, in the wrong hands, becomes a geopolitical weapon. Encryption can be broken, secrets revealed, national security strategies rewritten. That's why post-quantum cryptography has become a race in itself, a scramble to build algorithms resistant to quantum attacks before the threat becomes real. We're already seeing alliances and rivalries form around quantum research. Nations funding labs, corporations forming think tanks, universities launching quantum initiatives. The players see what's coming, and they're preparing. But what about the rest of us? What about the public? That's where storytelling matters. Podcasts like this, conversations online, accessible education, because if quantum computing is going to reshape the world, it can't be kept in the ivory towers. We need a public that's curious, informed, and ready to participate in shaping how this power is used, because power, without participation, always leads to imbalance. As we approach the final part of this episode, we'll step back from the theory and the hardware and ask a broader question. What happens to us as individuals, as a species, if quantum computing actually fulfills its promise? Stay tuned. We're almost there. This isn't just a new kind of processor. It's a new lens on reality. For centuries, our machines have mimicked how we think the universe works, step by step, logic by logic. Quantum computers flip that script. They reveal a world where things can be true and false at once, where causality is bent, where the act of observing changes the outcome. That's not just physics, that's a philosophical awakening. Because if our technology begins to reflect the strange, entangled, probabilistic nature of reality, then so must our minds, our approach to science may shift from seeking precise answers to embracing probabilistic truths. Our understanding of intelligence might evolve from deterministic predictions to context-aware decisions. Our systems of governance may need to adapt, not just to faster computing, but to deeper ambiguity. And maybe, just maybe, that's a good thing. Maybe the future isn't about solving every question, but learning how to live in the question. What kind of civilization do we become when we are no longer limited by linear processing? When our machines don't just extend our hands, but stretch our consciousness, that's where quantum computing could take us. Not just faster code, but a renaissance in thought. A chance to rewrite not only algorithms, but assumptions. Of course, none of this is guaranteed. The hardware is still young, the error rates are still high, the noise is loud. Many believe practical quantum computing at scale is still decades away. But history shows us that what seems impossible often arrives faster than we expect. And when it does, it doesn't just disrupt systems, it changes us. So we stand at the edge of something profound, not just a technological upgrade, but a metamorphosis in how we compute, how we understand, and how we imagine. And that's what this project, this podcast is really about. Not just reporting the headlines, but exploring the underlying transformation shaping our world. Thank you for being here with us today. This was Quantum Computers Are Useless? Project Metamorphosis podcast. And while quantum computers might seem useless now, the reality, as we've explored, is far more layered. If you found value in today's episode, help us grow this project. Like the video. Share it with someone curious. And most importantly, subscribe to stay updated with future episodes where we continue decoding the future, one idea at a time. We'll be back tomorrow with another deep dive into the emerging world of tomorrow. Until then, stay curious, stay critical. This is Project Metamorphosis. Signing off.